Hello, Edward from Enfield Physics Tutor here. Today a short video on centripetal force and acceleration. We're going to work through some of the maths and I'm going to show you some examples along with an exam question. So hopefully by the end you'll be all set up. We start by reminding ourselves that as the object moves around the circle, its velocity is constantly changing, not in magnitude but in direction, and this means that there must be an acceleration. By Newton 2, if there's an acceleration, there must be a resultant force. And of course the question is where is this force acting? I've asked a few students this question recently and they tend to come up with the same answer, so we're going to look at a couple of them and see why they might be wrong. One common idea is to suggest that the force is parallel to the velocity. This doesn't work though, because that's going to increase the acceleration in the same direction as the velocity, meaning that the actual value of v1, or that velocity, is going to increase as well. Another suggestion is to pick 2 points around the edge of the circle and just join them up with an arrow, and that'll be your direction of force. Which 2 points are you going to pick though? And even if you decided on them, you would of course still have a component in the y direction of that force that you've just imagined. And this y component of course will be parallel to your original velocity, therefore meaning it's going to increase in its magnitude as well. Having somewhat explosively dismissed several students' suggestions as to the direction of the force, I'm now going to use this diagram of a person spinning a mass on a piece of string above their head to demonstrate that it is in fact towards the centre of the circle. The arrow shows the direction of the force, and once you get used to this idea, it's not as strange as you might at first think. If we add a second point, then a third, and lastly a fourth, we can see that the force is always towards the centre. So at any point as the ball goes round the circle, there is a force pulling it inwards. And it is this force which causes the mass at any point around the circle to change its direction and therefore accelerate towards the centre. Interestingly, the word centripetal appears to be made up of two parts: centri, which probably has something to do with centre, and petal, which is an important part of a flower. Some rather complex mathematics leads us to the conclusion that this acceleration towards the centre of the circle, known as a centripetal acceleration, is calculated by using v squared over r. We know of course that if we multiply a by m, we get the force. Therefore we can find the centripetal force, or centripetal force, as being equal to mv squared over r. Recalling that the instantaneous velocity is equal to the angular velocity times the radius, we can then say that v squared is equal to omega squared r squared, and if we substitute for v squared in F equals mv squared over r, we will therefore get m omega squared r squared over r. And of course this simplifies down to m omega squared r. And so we find we have two versions for the force and acceleration towards the centre of our circle. It seems to me that one of the things students find hard in exam questions is identifying where exactly it is that the centripetal force is coming from. So we're going to look at a couple of examples of that now. Consider this diagram of the Earth orbiting the Sun. As I'm sure you know by now, there is an instantaneous velocity this way and a centripetal force acting towards the centre of the Sun from the centre of the Earth. And it is in fact the gravitational attraction between the two that causes the centripetal force in this case. And what about in this rather awesome example? As our skater goes around the circular half pipe, there is a reaction force which points towards the centre of that circle. See if you can visualise it now. In this question we are asked to find the tension in the string when the mass is at the bottom of its vertical orbit, in which it does 120 revolutions in a minute. Given that we're being asked to find the tension, and tension is a force, it would seem likely that calculating the centripetal force would be a good idea. And in order to do that we need a value for v. Now we can't find V directly because we don't know what omega is, so we have to calculate that too. So substituting the formulas for instantaneous velocity and omega together, we get that the instantaneous velocity is 2 pi r over t. But what's the period? Well, we're told that our object is orbiting 120 times in a minute, which means that it's doing 2 orbits per second, and therefore the period is half a second. Substituting in our values then, we find that V is equal to 3.14 meters per second, which is something of a coincidence. Using this value for velocity, we can now go on and calculate the centripetal force. Just by substituting in the values, we end up with a figure of about 79 newtons. And if this was a multiple choice question, you could bet your bottom dollar that 79 newtons would be one of the answers, though of course it is wrong. What if the bob is stationary? Would there be any tension in that string then? Well, of course there would. So the total tension in the string at the bottom is going to be equal to that provided by the centripetal force plus that created by the weight of the bob, which in this case is going to be 79 newtons plus 2 times 9.81. And when you do that, you get around about 99 newtons. Well, there it is. I hope you enjoyed our little trip round centripetal force and acceleration and that it was useful. Please don't forget to like this video, subscribe to the channel and share this video with all your physics related chums.